Okay, here we are back at my board, and I've got the function sketched out here. I've also got some tick marks on the x-axis. I'll get out of my way so you can see them here. And what we need right now is an algorithm. Now, an algorithm is basically a recipe for how to solve a problem numerically. We're not pushing symbols around on a piece of paper anymore. That's an analytical solution. A numerical one is where we're making calculations to estimate the answer. And I say estimate because when we're making calculations with a computer, we have finite precision. If I write square root of 2 down on a piece of paper, that's exact. If I calculate the square root of 2, I just type in MATLAB, it's SQRT, so you can pronounce that squirt if you want. But if I type in SQRT parenthesis 2 and hit return, I get a number. It's 1.414, whatever. And it goes out a large number of decimal places depending on how I format it. But it does stop. There is an end to it. Now, the square root of 2 is irrational. It goes on forever. And when I write square root of 2 down on a piece of paper, exact. But when I calculate it, my decimal places will end eventually because my computer has finite precision. So even though it's very close, it is an estimate. It is approximate. So remember, when you're doing numerical calculations, you are estimating an answer. Now, how close? Well, I don't know how close you want to get. Our estimate could be very, very close. And in practice, it's exact enough, if you can imagine that. So we need an algorithm, which is a clear set of instructions we can follow. And good algorithms have a couple of properties. The first is that they're easy to execute and the steps are unambiguous. The next is they converge on the correct solution. Another is that you can get them arbitrarily close to the correct solution. And another one, last one we'll talk about here, is that will also estimate your error for you. Not only will you have an estimate, you'll know pretty much how good that estimate is. Well, we're going to do something called the bisection algorithm. It has all of those properties. If there's one thing it's lacking, it's not very efficient. But everything else is there. It's a great learning tool. This is a great first algorithm to learn. So bisection is going to go in 2 steps. Step 1, we're going to start stepping forward to find approximately where the root is. We're going to step forward in steps, and we'll just call those delta x. Step 2, we'll iterate to reduce delta x, and delta x is going to be reduced by a factor of 2 every time. Every iteration will cut delta x in half. And so you can see that no matter how big delta x is when you start, if you cut it in half a couple of times, this starts to get small really quickly. You know, take 1/2 to the nth power. N doesn't have to be very big before the resulting number is really small. So iterate to reduce delta x. So that's all there is to it. And it's, like I said, a good learning algorithm for learning how to solve roots because it's simple. So let's start here by calculating roots as we move forward by delta x. So we need 2 things. We need a place to start, and we need to know what delta x is. This isn't calculus anymore. There's no infinitesimals or unknown numbers anywhere. We know what all the numbers are. So we're going to say x0 equals 0. We're just going to start right there. Yeah, I've sketched this out, but let's pretend we don't know what the answer is, or we don't know what this curve looks like. If we knew what it looked like, we wouldn't have a problem. So we'll set delta x equal to 0, and this is a guess, all right? Doesn't have to be a good one. And we'll set delta x equal to 1, also a guess. You know, because you don't know what these are, you're going to have to guess some of these numbers. Now, if you guess badly, all that happens is you wind up doing a few more calculations, so it's not that big a deal. Delta isn't very good. That's better. So what I'm going to do here is start here, and say I'm going to find f of x0. All right, it's going to be a negative number. F of x1, also a negative number. F of x2, also a negative number. 3, 4, 5, 6. Wait a minute, I got a positive number. Now, how do I tell the computer, how does the algorithm know that I've crossed the x-axis? Well, I'm going to calculate f of 0 and f of 1, multiply them together. If I get a positive number, I didn't cross the axis. The only way that product would be negative is if one of these two numbers were negative and one was positive. Okay, right there, both negative, both negative, both negative, both negative, bang. One of them's negative, one of them's positive. And this is x equals 5, and that's x equals 6. So until I got to those 2 points, all my roots were negative. When I multiplied, and I'll write this out, f of x 5 times f of x 6. I'll do this wrong. Where's my, here it is. Less than 0. That means I've crossed the axis. Okay, so that's step 1 done. Now I'm going to just walk you through it in words here, and then we're going to go on to the MATLAB, and I'll show you how to calculate it step by step. So we've got that part done. Now we're going to iterate to reduce x. Well, how are we going to do that? Well, give me a second here. I'm going to erase the board to get us some real estate back here, and I'll sketch this out for us. Okay, I've zoomed in quite a bit here. And right now, the only thing we know is that the root lives between 5 and 6. Our estimate now, oops, there we go. I get that right? Yeah. X is in the range from 5 to 6. We don't know where it is there. We only know it's between those two numbers. So what are we going to do? Delta x equals delta x over 2, so now it's 0.5, right? Which is going to be right there at 5.5. So now I already know f of 5. It's already been calculated. Now remember, the game we're trying to play here is we're trying to find the root in as few calculations as possible. That's what most algorithms are trying to do. When you talk about how efficient an algorithm is, what you're really talking about is how many clock cycles does it take to get you to the right answer? And no number is too small. You know, 1, I guess, is the right answer. But we're trying to get the solution as few calculations as possible. In this case, the function is so simple, it doesn't really matter. If we had to do 1,000,000 calculations, it wouldn't matter. In practice, sometimes calculating the value of the function is extremely expensive. It might be the result of some very, very sophisticated calculation. And so you can't afford to evaluate the function any more times than you need to. So efficiency is where it's at. So let's see, f of 5 times f of 5.5. Okay, these are both negative, so that's still greater than 0. I know the root isn't there. Let's try something else. Let's go f 5.5 times f of 6. That is less than 0. There. Now I know the root is between 5.5 and 6. Well, let's update our estimate now. I'm going to erase some stuff here. .25 now is our delta x. We cut it in half again. We bisected it. Now I know the root lives between 5.5 and 6. So I don't need this anymore. Okay, going to do this again. Now, this isn't to the right scale here. This is actually, I'm going to correct this. Let me just fix this for us. I know that the root is actually like 5 point, what I decided it was, almost 5.9. So I'll draw it like that for right now. But we make the point, we're going to go through this algorithm one more time. Well, what's the next midpoint I need? Well, that's 5.75, because delta x is now a quarter. It was a half. So now I know it's somewhere in there. Let's calculate again. Well, let's see. F of 5.5, which we already know. We've already calculated that, so we don't need to calculate it again. This doesn't cost anything, and this doesn't cost anything. We already know that what F of 6 is. So those are both free. This is the only new one we have to calculate. Okay, F of 5.5 times F of 5.75, still greater than 0, because both of those are negative. A negative times a negative is a positive. Let's try this again. F 5.75 times F of 6. Ah, look at that. There. Looks like I gave you a smiley face before. I should do it again. There. All right, got it again. So now I know it lives between here. Well, let's do this again. And so it goes. We can keep doing this as long as we want. And this range, where the answer lives, keeps going down by half. Now, right now, we only know that the answer lives between those two numbers. We don't know where it is. But we can arbitrarily make this as small as we want. Just keep dividing and dividing and dividing and dividing. And eventually, you'll get down to the point where you don't care anymore. Well, this is an important point here. When should the algorithm stop? Because, in theory here we could go forever, although we'll run out of significant digits in the computer. But we could go quite a ways before we ran MATLAB out of significant digits. It does finite precision calculations, but there's a lot of decimal places there. For the sake of efficiency, we want to stop when the answer is precise enough. Precise enough. What does that mean? Well, it depends completely on the problem. It depends on how precise an answer you need. Let's take something simple. Let's say you're calculating the stall speed of an airplane. Well, how precise a number do you need? Do you need to go out to 5th, 6th, 7th, 8th decimal place? Probably not. None of your instruments are that good. I don't know what a pilot's ability is to control the speed of an airplane, but I'm guessing millimeters per second is not on the menu. If you knew the answer to within a couple of meters per second, that might be enough, but maybe you'd calculate it to a few tenths. That's certainly enough for any practical purpose if you're actually going out on a flight test. You can't control the speed of an airplane that closely. You probably can't even measure it that closely. The wind is not, you're not flying through a uniform, still field of air. There's gusts and winds and all kinds of things. So maybe in that case, if you knew the answer to, I don't know, 0.5 meter per second or so, that would be fine. What if you were trying to calculate, I don't know, the location of a laser in an interferometer? Well, now a millimeter is an awful lot. Maybe microns? In that case, you really do need 6, 7, 8, 9 decimal places, perhaps. The other thing to keep in mind is how good is your model? If your model is good to a couple of percent, and you're trying to calculate to a small fraction of 1%, well, mathematically it's okay, but you're calculating past the precision of your model, so you need to stop then. And how this looks in algorithms is there's a tolerance usually inside the algorithm that says when the change in your answer gets smaller than this tolerance, whatever it is, stop. There's a default built into fsolve or F0, and you can go in and you can change that tolerance if you need to. So with that, let's go to MATLAB on my screen again and let's wrap this up.